Hello, Math Humans. We're going to do 9.3 today. We're going to be talking about geometric sequences and series. So our objectives are that today we're going to define a geometric sequence. We're going to write the rule and find the nth term of the sequence, and then we're going to find partial and infinite geometric series, which means sums. All right, so a geometric sequence is a sequence where the consecutive terms change by a common ratio. Remember that for arithmetic, we had a common difference. Now we have a common ratio, which means that I am multiplying or dividing by the same amount. So a common ratio is called R, and it is new divided by old. So when we write our generic term, or our rule to create a geometric series, notice that here is the formula. It is a sub 1. Remember that a sub 1 is the first term. R is going to be your common ratio. And then remember that n is always going to represent the number's position. So let's just jump right in with our first example. So example number 1 says write the first 5 terms of a geometric sequence and it's going to say whose first term is going to be 3 and whose common ratio, so much writing, whose common ratio is 2. And then I want to graph it and look at it. Alrighty? Okay, so I know that my formula is a sub n is equal to a sub 1 times r raised to the n minus 1. So our generic term is going to be, first term is 3, so it's going to be 3 times the common ratio is 2 raised to the n minus 1. And I could generate these terms by hand, but I am going to use my handy dandy grapher. So I'm going to make sure that my calculator is in sequence mode. And I'm going to go to my y equals, and I'm going to clear these lines, because remember, it takes 1, 2, 3 lines to put in a sequence. So when I enter my rule, I'm going to do 3 times 2 raised to the n minus 1. I don't have to put in the third line because I've already told it what the first term is. So I'm going to quit. I'm going to do second U, and I'm going to do 1, 5, remembering that the comma lives up above the 7, and I hit enter, and it generates my terms for me. When I report, I could do A 1, 5. I could also do A 1, 2, 5. Either is appropriate, and I'm going to get the 3, 6, 12, 24, and 48. So that was actually pretty easy. We could do it by hand as well, but sometimes it's just as nice to do it in our calculator. So then I'm going to hit graph, and I'm going to do a zoom 3 enter, so I can zoom out. Oh, I lied. Zoom 2 enter. I want to zoom in a little bit. Zoom 2 enter. Zoom 0. There we go. Y equals, okay. So the thing to notice about our graph is technically it's not connected, so I need to change a setting on my grapher so that the dots aren't connected, so that it's giving me individual data terms and not connected data terms. But the thing that's important to notice is that I have a curve and not a slope. So, sorry, I guess that's bad math terms. I don't have a straight line. I have a nice little curve. And the reason that my curve is jerky is because it's each one of the vertices is going to be a data point. All right, so the thing to notice about a geometric sequence is that it is a curve and not a straight line. All right, let's do our next example. So example number 2. And this one says find the 15th term of the geometric sequence. Remember, sequence is a collection of terms, of individual terms. A series is a sum of terms whose first term is 20 and whose common ratio is 1.05. So on almost all sequence problems, the first thing that you need to do is write the rule, because that's going to help us find what we need. So I'm going to do a sub n is equal to, remember it is r raised to the n minus 1. I know my first term, and it tells me that my first term is 20. It tells me that r is 1.05, and I'm going to raise that to the n minus 1. Okay, so I'm actually going to do this one by hand. I'll show you how to do it in your calculator, but I'm going to also do this one by hand. It wants the 15th term. So a sub 15 is going to equal the 20 times the 1.05 raised to the 14 minus 1. And if I do that math in, bad math, this is 15 minus 1, so that means this is 20 times the 1.05 raised to the 14. My brain and mouth aren't working at the same speed. I can just put this in my grapher, and then I can get a solution as 39.60. I will tell you, if you do that part by hand, if I quit, I need to do 20 times 1.05 raised to the 14, and then there is my solution. My preference is always that you give 3 decimals, so I would have written this as 39.599, and then that would be appropriate, because in big kid math we always report to 3 decimal places. Our book sometimes only reports to 2. You could do this in your grapher as well by entering 20 and then times the 1.05 raised to the n minus 1, and then quit, and then do second u, and I want the 15th term, and there we go. So you can also do it using the sequence mode of your calculator. Alrighty. So as we move along, let's do another example. We'll do, we're going to make our paper look like Christmas. We got red and green going on. Example 3, I want to find the 12th term of the sequence. And we're going to have, the sequence is 5, 15, 45, ... And then, as before I finish talking about the sequence, it takes at least 3 terms to define a sequence. So if you have 2 terms, that's not enough information, but it always takes at least 3 terms to define a sequence. So if I want to find the 12th term, before I can write a rule, the first thing I have to do is find r. So r is new divided by old. Okay, so that's going to be, I'm just going to do it twice to show that it's the same. So 15 divided by 5 is 3. I could have done 45 divided by 15. I would also have gotten 3. If the r value is not the same, then it's not a geometric sequence. Okay, I know a sub 1. I know r, so now I can write my rule. A sub n is a sub 1 times r raised to the n minus 1. So this is 5 times 3 raised to the n minus 1. And again, I'm going to do this one by hand just to illustrate a point. So a sub 12 is going to equal 5 times 3, 12 minus 1. So this is 5 times 3 raised to the 11. And when I do that math, I get 885, 735. And I would report a sub 12 is 885, 735, because remember, every single solution that you write has to be identified. All right, let me move my little thingy because my paper is in the way. So let's do our next example, example number 4. This one's going to be a little bit more entertaining. Actually, I'm just going to go to a whole new page because this example is going to burn a little bit more paper. So example number 4 says the 4th term except I forgot the word term of a geometric sequence. They will usually tell you what type of sequence it is unless they give you the full sequence and they're asking you to figure out what type of sequence it is. The 10th term of the geometric sequence is 125 divided by 64, and I want to find the 14th term. Okay? All right. So let's write down what we know. We know that the fourth term, so a sub 4, is going to equal 125, and I know a sub 10 is equal to 125 over 64. So I'm going to use one of these terms to see if I can write a system of equations. So I'm going to write, remember our generic rule is a sub 1 times r raised to the n minus 1. So using this data point, I'm going to write 125 is equal to a sub 1, I don't know a sub 1, times r raised to the 4 minus 1. So this is a sub 1 times r to the third. I'm going to also write a second equation using a sub 10. So 125 over 64 is equal to a sub 1 times r raised to the 10 minus 1. So I have a sub 1 times r, and I'm going to raise that to the 9th. Okay? All right. So I'm actually going to take this 64 to the other side of the equation. Do I want to do that yet? Maybe not. So I have two equations, and I have two variables that I don't know. I don't know a sub 1, and I don't know r. So what I'm going to do is solve both equations for a sub 1. So in the first equation, I get a sub 1 is equal to 125 over r to the third. And in this equation, I'm going to get a sub 1 is equal to 125 over 64 r to the 9. Well, the two a sub 1s are equal. This is just very similar to problems that we've done before. So I'm going to set these two equations equal. So I get 125 over r to the third is equal to 125 over 64 r to the 9. I'm going to cross multiply. So I'm going to get r to the third times 125 is equal to 125 times 64 r to the 9th. I'm going to put the numbers together, and I want to put the r's together. So I'm going to get 125 divided by 125 times 64 is equal to r to the 9th divided by r to the third, which is r to the 6th. Because if the bases are the same, you subtract. The 125s are going to cancel, so this is going to equal 1 over 64. So now I can solve for r by taking the 6th root of this. So I'm going to say that r is equal to the 6th root of 1 divided by 64. I'm going to push buttons on my calculator to find that, and I get 0.50. Well, that was polite. Well, now that I know r, I can find a sub 1. And it doesn't matter which equation I use. I'm just going to use the first one because it's what I came to. So I have 0.5 raised to the third. And when I do that math, I'm going to get 1,000. Well, now I know a sub 1. So I'm going to circle that guy just so we don't lose it. And I know r. Okay. So now I can write my rule, because all we've done at this point is just get to the point where we can write the rule. Remember, it's a sub 1 times r raised to the n minus 1. So it's going to be 1,000 times the rate, which is 0.50 raised to the n minus 1. And I want to generate the 14th term, so a sub 14 is going to equal the 1,000 times 0.50 raised to the 14 minus 1. When I do that math, you're going to get 125 over 1024. Now, you probably would have gotten a decimal when you did this, and then I math fracked it. So math frac is a glorious button on your calculator. Let me just illustrate that really quickly. So I'm going to have, what they say, 1,000 times 0.5 raised to the 13, right? So there's my 13, and I got a decimal. and then I just hit math, frac, enter, and there is my nice little fraction, okay, and they reduced it even more. So then we would have that this is 25 over 2048, okay. Sad day, I entered it badly, wrong statement, so I have 1,000 times 0.5 raised to the, what number did I raise it to, the 13? And then I'm going to math frac it. Oh, there we go. There's our cool little answer. So I was right the first time. Whew, sometimes brain farts happen. All right, let's keep moving and start talking about sums. All righty. So the sum of a finite, and remember finite means it has a definite beginning and a definite end, geometric series, is going to be of the formula S sub n is equal to the sum from I equals 1 to n of a sub 1 times r to the I minus 1, okay? Well, we don't want to have to use this function on our calculator, so we're going to use a handy-dandy formula that says a sub n is equal to a sub 1 times 1 minus r raised to the n over 1 minus r, alrighty? So this is for a finite geometric series. Again, we have to talk about the variables because sometimes the variables get confusing. This says I want to do a partial sum. How many terms am I summing? So n is how many terms are you summing? Got some nice Harry Potter playing in the background. A sub 1 is going to be the first term of the summation. R is definitely going to be your rate of change, right? So R is just going to be R. And then N, we've already talked about, is how many terms we're summing. You do have to be careful when you put this in your calculator because you want to make sure that the whole numerator is in parentheses and that the whole denominator is in parentheses. Alrighty. The other formula that we're going to get is the sum of an infinite geometric series, okay? And remember that infinite means that it would be S sub n is equal to the sum I equals 1 to infinity of a sub 1 times r raised to the I minus 1, okay? So in an infinite geometric series, it has a caveat, meaning it has a special condition. And it means that the absolute value of r, because it doesn't matter whether the series is increasing or decreasing, it would decrease if r is negative, but r has to be less than 1. The absolute value of r has to be less than 1. If not, then the series is not possible. So if this is true, then S sub n is going to equal a sub 1 divided by 1 minus r. So it's actually a really simple formula. A sub 1, remember, is again the first term of your summation. It's not necessarily the first term of the sequence. It's the first term of the summation, and then I'm going to divide by 1 minus r. This is the key element right here. If the absolute value of r is not less than 1, then the geometric sum is not possible. So let's do an example. So I think we're on example number 5, and I want to sum I equals 1 to 12, to 12, of 4 times 0.3 to the I minus 1. So sometimes this is the first term, but depending on where you're starting, you need to actually do the math to figure out your first term. So you don't assume that your a sub 1 is going to equal that first term because it depends on where we start and what the rule has here. So I'm actually going to calculate a sub 1, and it would be 4 times 0.3 to the 1 minus 1, 0.3 to the 0. Anything raised to the 0 power is 1. So it is actually my first term, but you can't assume that always. because, again, it depends on where I start my summation. Alrighty, let me bring my computer back. Alright, I hate it when it goes away. So when I start my summation, my R is 0.3, which is less than 1. So that means that my sum is going to be, oops, sorry, bad math, wrong equation. So I'm doing a finite sum, shame on me, S sub n is equal to a sub 1 times 1 minus r to the n divided by 1 minus r. My first term is 4. I have 1 minus, and then my 0.3. 12 minus 1 is 11, plus 1 is 12, so I'm summing 12 terms. Remember, it's always the top index minus the bottom index plus 1 over 1 minus 0.3. I put that in my calculator carefully, and I would get that the 12th sum is equal to 5.714. Okay, let me move my paper up so you can see that. So that would be how I report my solution. S sub 12, because I'm taking the 12th partial sum, is equal to 5.714. Okay? All right, I have 2 more examples, and then we are done. Example number 6. Ooh, that's a lot of examples today. I want to find the sum from n equals 0 to infinity of 4 times 0.6 raised to the n. So this is an infinite sum, which means I'm going to be using the formula S sub n is a sub 1 over 1 minus r, with the caveat that r has to be less than 1. Well, this is my r, and r is less than 1. Notice on this one that I'm starting at 0. So my a sub 1 is going to equal 4 times the 0.6 raised to the 0. Anything raised to the 0 is 1, so it's 4. I know that in both of the examples this has turned out, but if I started summing, say, at the 25th term, that, remember, a sub 1 is the first term of the summation. So we want to make sure that we calculate this every time and not make assumptions. So the infinite sum is going to equal my first term 4 divided by 1 minus 0.6, and when I do that math I get 10, and then I report S sub infinity is equal to 10. So that's actually nice and polite and easy to report. All right, last example. Woohoo! Example number 7 says find the sum, and I want to have 3 plus 0.3 plus 0.03 plus 0.003 plus ... Notice that they've given it to you in a different format. And notice that I'm starting at 3 and I go to infinity. So I want an infinite sum. I need to know what's r because I need to know if the infinite sum is even possible. So I'm going to calculate r. Remember that r is new divided by old. So I'm going to take the 0.3 and divide by 3, and I'm going to get 0.10. And I'm just going to check it with another one. And if I did 0.03 divided by 0.3, I'm still going to get 0.10. Notice that r is less than 1, so then I can actually calculate my infinite sum. So my infinite sum is going to equal the first term of the summation divided by 1 minus 0.10. This is 3 divided by 0.9, and this turns out to be 3.333 repeating. Alrighty, so my infinite sum is going to be 3.333. Alright, that's it for today. Thank you for your patience, and I will see you soon.